What if everything we thought we knew about, the fundamental nature of spin in materials, what if it was just a surface-level approximation?
Mm.
And what if there was something deeper? A unifying force connecting spin, space-time, matter, maybe even consciousness.
That's a pretty mind-bending place to start.
It is. Welcome to the Deep Dive. I'm your guide, and today we're diving deep into a really revolutionary framework. It's called the Unified Coherence Theory of Everything, or UCTE.
And our source material today is a, well, truly groundbreaking document. It's by Philip Randolph Lillian, titled Coherence Curvature in Quantum Materials, a Unified Coherence Theory Perspective.
Yeah, foundational is the right word.
Definitely. It offers a completely fresh lens, really, to view the quantum world.
So our mission for this deep dive is to really explore comprehensively how this UCTE fundamentally redefines our understanding of quantum materials.
Right. It's not just tweaking existing theories.
No, exactly. The author calls it a generative explanation. It tries to explain how these properties actually arise from first principles.
And it also provides a predictive framework for quantum control and even intelligent material design. Big claims.
Huge claims.
Right.
So we're going to share the intricate details, the overall explanations behind this new paradigm. We want you to grasp the full scope of what it's suggesting.
And hopefully by the end of this, you'll have gained, well, a shortcut to understanding these incredibly complex, cutting-edge ideas.
Yeah, uncover some surprising facts, maybe have a few aha moments.
Mm-hmm. Illuminating a scientific frontier that hints at some really powerful future applications, stuff that could potentially redefine technology as we know it.
Okay, let's unpack this. When we say the UCTE isn't just another theory, we really mean it. It introduces some really fundamental shifts in how we even think about solid-state physics.
It's an ontological redefinition, as the source puts it.
Exactly, ontological. It's rethinking the very building blocks of reality at this level. Conventional physics often talks about emergent properties.
Right, things that arise from particles interacting.
Yeah, almost like an afterthought sometimes. But UCTE seems to flip that perspective completely.
Well, what's truly fascinating here, I think, is how the UCTE directly tackles these profound limitations in conventional models, things physicists have wrestled with for, well, decades.
Things that just didn't quite fit.
Exactly. And instead of just offering approximations or, adding more complex terms to old equations, it proposes a deeper underlying structure.
Like a foundation?
A geometric and ontological structure, yeah, for materials and their properties. It aims to replace these sort of fragmented, piecemeal approaches
with something unified.
A truly coherent, unified framework. One that explains phenomena from the ground up, moving beyond just describing things to a truly generative understanding, explaining why.
And one of the most radical redefinitions it proposes is how we understand spin.
Ah, yes, spin.
Conventionally, we're taught spin is primitive, right?
Yeah.
An intrinsic property of a particle, like an electron.
Tracking there. Fundamental. Unchanging.
But the UCTE says, hold on, maybe not. It suggests spin isn't primitive at all. Instead, it posits that spin is a, quote, reduced projection of a deeper bivector coherence tensor. Soon.
Okay, that's a mouthful.
It is. Can you help us get our heads around what a bivector coherence tensor actually means here? And why seeing spin as just a projection is such a game changer?
Absolutely. Let's try. Imagine reality not as just particles, but as a complex sort of twisting fabric, a continuous dynamic field.
Okay, like a field, not just points.
Right. The bivector coherence tensor soon is like the fundamental twist or orientation within that fabric. It's an antisymmetric field, meaning it describes a kind of intrinsic rotation or circulation. Think maybe like how an electromagnetic field describes forces, but this describes, well, coherence.
Okay, so it's the underlying structure.
It is. So when we observe spin in an electron, that measurable spin, so the UCTE says that's not the fundamental thing itself.
It's not.
No. It's like, imagine seeing the shadow of a complex 3D object cast onto a 2D wall.
Ah, okay. The shadow's real, you can measure it.
Exactly. It's a real observation, but it's just a projection of something much deeper, more fundamental. This underlying coherence field, say.
And why is that so profound?
Because it potentially bridges this long-standing gap in physics. You've got, on one hand, macroscopic band structure modeling.
How electrons behave in materials, usually simplified.
Right, often using effective models. And on the other hand, you have fundamental field theory describing basic particles and forces.
And they didn't always connect well?
They often felt disconnected, yeah, like speaking different languages. But by showing spin emerges from this deeper, unified coherence field, UCTE provides what it calls ontological continuity.
Ontological continuity.
It basically says, look, these aren't separate explanations. They're derived from this common fundamental coherence. It provides a foundational link where before we often had sort of ad hoc connections, you know?
Okay, that makes sense. So if spin is a projection,
Yeah.
what is doing the projecting? What is this underlying fabric you mentioned?
Well, that leads us right to the UCTE's central concept, coherence itself.
Coherence, not just like, laser beam.
No, much more fundamental. It's presented not just as a state, but as a fundamental generative force underlying all material properties. It's the fabric from which everything emerges, according to this theory.
Wow.
And this is a key distinguishing feature of UCTE. It's described as a foundational framework unifying spin, space-time, matter, and consciousness via coherence dynamics.
Consciousness, too. That's ambitious.
Extremely ambitious. Now, just to be clear, our deep dive today is focusing mainly on the quantum materials aspect, which is really detailed in the source.
Right.
The consciousness part points to UCTE's broader goal as a theory of everything. It suggests even consciousness might be rooted in these same coherence dynamics, but that's a whole other conversation, probably even more mind-bending.
Definitely one for another day.
For now, the key takeaway is that UCTE suggests coherence isn't just an emergent property of quantum mechanics, but the very operator that generates observed reality. It's the unifying principle.
Okay, coherence is the generator. Got it. And if that wasn't enough, UCTE also tackles this known problem in conventional models, the reliance on orbital angular momentum, L.
Ah, yes. LC, standard stuff.
Standard but problematic. The UCTE says these models break down in periodic solids and lead to fragmented approximations. Why?
Well, think about a crystal lattice. Electrons aren't neat little particles with a definite position R and momentum P like in classical physics.
Or waves spread out.
Exactly. Their wave nature extends across the crystal. So that classical definition of L, R cross P, becomes really problematic. It leads to inconsistencies, a lack of universality in predictions. It just doesn't quite work smoothly.
So how does UCTE fix this?
It offers a pretty elegant solution, actually, and mathematically consistent, which is key. It replaces these fragmented approximations with a fundamental geometric and ontological structure.
Okay.
So instead of forcing the classical L concept where it doesn't really fit, it substitutes it with what it calls the intrinsically defined bivector projection, BEK.
Oh, the new term.
Right. This is a projection of that fundamental bivector tensor seen, but specifically in momentum space, K-space, and critically interacting with the crystal symmetry.
And the crucial part.
The crucial part is that this K field preserves translational symmetry.
Ah, that's vital for crystals.
Absolutely vital. Electron wave functions in crystals, block waves, must have the same periodicity as the lattice. Preserving the symmetry means the UCTE framework avoids those breakdowns you see in conventional approaches. It's a really significant step, mathematically and conceptually. Provides a universal, robust description.
This seems to lead us directly to the real star of the show for understanding quantum materials in this framework, the Coherence Curvature tensor.
Yeah.
The source highlights this as the core innovation. It directly replaces those ill-defined orbital angular momentum operators in periodic systems,
giving us a proper, consistent way to describe these interactions without those problematic approximations.
And this tensor, it isn't just math, right? It governs actual physical behavior.
Absolutely. It's the definitive entity that governs three primary functions, defining the very behavior of quantum materials according to UCTE.
Okay, what are they?
First, it dictates spin transport as torsional coherence flows.
Torsional coherence flows.
Yeah.
Like a twisting current.
Exactly. Imagine spin flowing not as particles moving, but as this complex, twisting dynamic field of coherence, like a spiral in a river.
Okay, number one. What else?
Second, it explains topological phase transitions as winding jumps in curvature structure.
Winding jumps. So big changes in material phases.
Especially those robust topological ones.
Yeah.
UCTE says they happen because of sudden quantized shifts or jumps in the underlying geometry of this coherence field, not just smooth changes in energy.
Like flipping a switch in the geometry.
Kind of, yeah.
Yeah.
And third, it enables a completely new way of material classification by curvature quantization, not symmetry breaking.
Whoa, okay, that's different. We usually classify based on symmetry.
Right. This is a major departure. Moving from describing broken symmetries to a generative classification based on the fundamental coherence geometry itself.
So instead of thinking about materials having properties that emerge when symmetry breaks, UCTE talks about this curvature as a torsional landscape over the Brillouin zone.
Exactly. The Brillouin zone is that fundamental map in momentum space for electrons in a crystal.
Right.
So picture a landscape, maybe like mountains and valleys, but its twists and turns, its actual geometry is this coherence curvature.
So the landscape is the property, in a way.
In a fundamental way, yes. It's not an emergent byproduct of band theory. It's presented as the foundational geometry of coherence dynamics. The landscape itself, the torsion or twistiness, fundamentally determines the material's properties. Like the shape of the terrain dictates where rivers flow.
Okay, this is a lot to take in. Maybe we should nail down some of these key terms. To really grasp UCTE, we need to get comfortable with its core vocabulary.
That's a good idea. It helps understand how these new terms precisely define the phenomena. Appreciating the definitions is key to seeing the depth of UCTE's generative explanation. They aren't just new labels, they define the building blocks.
Right. Think of this next part as your essential guide to navigating this new landscape. So first, UCTE itself. Unified coherence theory of everything.
Right. The big framework aiming to unify spin, space-time, matter, and yes, consciousness through coherence dynamics.
And we touched on the Bivector coherence tensor or something.
Yep, that's the fundamental antisymmetric coherence field, the source from which spin and transport effects are reduced or projected, the primary underlying field.
Okay. Then you mentioned the spin lattice coupling field, BJ.
Yes. This is the crucial step connecting the abstract soon to real materials. It's the momentum space projection of soon specifically interacting with the crystal symmetry.
Mathematically it was.
That's the one. PIACO is a coherence-preserving projection onto the block basis. Conceptually, it describes how the fundamental coherence field is shaped by the crystal's atomic arrangement. And crucially, it preserves that block periodicity, avoiding those theoretical issues.
And building directly on BCO, we get back to the main player. Coherence curvature, AJ.
The field strength of BIAG, exactly. This is the mathematical object that defines the torsional structure, the topological properties.
The equation was AJ, BJ, EdgeBia plus EdgeBB. Looks complicated.
Well, let's break it down slightly. The source notes the first two terms, the derivatives, are abelian. Think linear coherence torsion, like a simple uniform twist.
Okay.
But that third term, abbibishi, that's non-abelian. That's where the complex interactions between different components of the Bivector field itself come in. It leads to nonlinear effects, real richness.
Then it plays a role like Berry curvature in normal physics.
Analogous, yes. Berry curvature describes how wave functions change as electrons move in momentum space. But here, Asia arises ontologically from the fundamental bivector coherence itself, not just from emergent band properties. It's deeper.
Got it. Then flowing from that, the Chern number, KK.
A key topological invariant. It's the quantized integral of this curvature across the whole Brillouin zone. KBZ exia dA.
Quantized means it only takes integer values, like 0, 1, -1.
Exactly. It jumps in discrete steps. This number quantifies the net twistiness or coherence torsion flux through the Brillouin zone. It's a robust way to classify the topological phase. If K changes, you've had a fundamental topological phase transition.
And coherence torsion itself just refers to that twisting.
Yep, the local or global twisting of the coherence field. And importantly, this twisting is presented as directly responsible for those robust topological transport effects, why charge or spin moves in specific protected ways.
Okay. What about the Bianchi identity? Sounds important.
It is, for mathematical consistency. It's a tensor identity ensuring the curvature fields are conserved and integrable. Basically, it guarantees that the coherence curvature behaves in a physically sensible way, that the torsional coherence residues are conserved. A fundamental check.
Makes sense.
Wow.
Then there's flat band coherence.
Yeah. A fascinating phase where the curvature agent just vanishes over wide areas of momentum space.
Zero twisting.
Essentially, yeah. This allows for phase-locked coherence domains, a very stable state where coherence is uniform, minimal flow. Especially very useful.
Why useful?
Well, flat bands often enhance electron interactions, which can lead to exotic stuff like high-temperature superconductivity or weird magnetism.
Interesting. And a wheel node.
That's described as a coherence monopole in K-space. A singularity, a point where the coherence field acts like a source or sink for the bivector field, a topological defect, really.
Like a magnetic monopole, but for coherence.
Sort of analogous, yeah. And these nodes are predicted to have major effects on electronic properties, creating conductive surface states or unique responses.
Okay, curvature evolution. This sounds practical.
It is. It's all about how Asia changes when you perturb the material, apply strain, dope it, add fields. Understanding this evolution is absolutely central to the whole idea of quantum control and intelligent material design.
Right, designing materials intelligently.
Exactly.
And finally, a coherence engine.
This isn't abstract theory, it's a potential application. A material or device designed to explicitly harness these coherence fields for energy, information, or even changing the material's structure, where the theory meets technology.
Okay, that glossary helps anchor things.
Yeah.
So now, here's where it gets really interesting, I think. UCTE isn't just definitions. It claims to provide a unified explanation for a whole range of quantum phenomena we actually see in labs.
Right. It tries to bring seemingly separate effects under one conceptual roof, explaining them all through this lens of coherence curvature.
It connects to the bigger picture, offering this generative framework, redefining how we classify materials and understand why they do what they do.
It's a shift from just describing phenomena to explaining their fundamental origins via the geometry of coherence.
Let's start with spin transport. We said it becomes a coherence flow across torsional gradients.
Yeah, spin current isn't just electrons carrying spin. It's a visible effect of a twisting current in the underlying coherence field.
And there's even a formula, G spun EDO, AAEFKEK.
Right. And that formula generalizes things like the spin Hall effect and anomalous Hall effect. It reinterprets them as direct results of this torsional coherence flow, not just, say, side effects of spin-orbit coupling.
So the spin movement is intrinsic to the field's geometry.
That's the idea, which is a huge shift, really. It gives new ways to think about predicting and controlling spintronics.
And this leads straight into that paradigm shift in classifying materials. Not by symmetry breaking anymore.
Correct. Classification by coherence curvature topologies and curvature quantization. The fundamental geometry and its quantized properties define the phase, a more fundamental approach.
So what are the specific signatures for different phases? Let's take topological insulators, TIs, insulating inside, conducting outside.
For TIs, UCTE sees them having non-zero exia even in time reversal symmetric systems.
Even with symmetry, that's unusual.
It is. It's interpreted as bivector phase windings preserved under symmetry. So think of the underlying coherence field having this robust, non-trivial twistiness that's protected, leading to those surface states. The conduction is a direct result of that geometric winding.
Okay. What about churn insulators?
Defined by quantized total curvature yet ZZ. That integer z, the churn number, comes from the total twistiness integrated over the whole Brillouin zone.
And that number relates to edge states.
Directly. It's seen as coherence integrated chirality across the Brillouin zone. The topological property and its observable effects arise straight from this integrated geometric winding.
While semimetals, those exotic ones.
Characterized by singularities in BK, those curvature monopoles.
The coherence monopoles.
Was interpreted as bivector splitting points across coherence domain walls. Points in momentum space where the coherence field effectively splits or annihilates. These singularities are the origin of their unusual transport properties.
Anomalous Hall-Metals Hall effect with no external B field.
UCTE attributes this to non-zero curvature, broken inversion time symmetry. This creates a coherence torsion bias. The twisting is skewed in one direction, and that directly causes the non-reciprocal flows observed.
Okay. Spin Hall materials. Generating spin current from charge current.
Characterized by opposite sign curvatures for spin up-down.
Opposite twists for different spins.
That's the interpretation, by vector projected dual coherence channels. This intrinsic opposite twisting drives the spin separation, causing the spin Hall effect.
Topological superconductors.
Described as phase-locked BB with curvature boundary nodes, reflecting bivector coherence phase locking across multiple fermions. The coherence isn't just in the electron pairs, but in the underlying field itself, leading to superconductivity and exotic boundary states like Majoranas.
And finally, flat band materials again.
Where coherence curvature vanishes over wide zones, indicating residual symmetry stabilization of coherence with minimal flow. The lack of twist quenches kinetic energy, enhances interactions, potentially leading to high TC-SC or novel magnetism. The flat coherence landscape helps collective states form.
So the big unifying insight is all these conventional phases, metal, insulator, topological, they're just downstream effects of coherence curvature classes.
Exactly. The observable phases aren't fundamental themselves, but consequences of how the underlying coherence curvature behaves its topology, its quantization.
And all spin transport effects, Edelstein, Xie, Xie, they all derive from the structure of BN.
One single origin for a whole zoo of complex quantum phenomena. It's elegant, if nothing else.
So it's not just a better approximation, it's a total reframing. The source says topological classification is a consequence of hyperfractal coherence resonance reduction, not symmetry breaking.
Yeah, that's a mouthful.
It really is.
Conceptually, it suggests a deeper, more intricate, fundamentally geometric origin, like a complex fractal where patterns emerge from rules at every scale. Topology isn't just about symmetry changing, but about the fundamental coherence resonating in specific ways that then reduce down to what we observe.
Wow. Does this framework make testable predictions?
Crucially, yes, that's vital. For example, it predicts measurable spin-Hall connectivities are linked to net torsion in IJA.
Yeah.
That's a direct connotative link experimenters can check.
Okay.
It predicts sharp transitions occur when bivector phase windings shift across coherence resonance thresholds, giving precise markers for phase changes.
And the control aspect.
Yes, lattice perturbations like strain or twist modulate the coherence curvature landscape. This is powerful. It enables control of transport via this intelligent field engineering. We're not just observing, we can potentially design and control.
Okay, so this brings us to the what does it mean for us part?
Yeah.
The future, the applications. This isn't just understanding, it's about control.
Exactly. UCTE offers a blueprint for intelligent material design and curvature field engineering, moving beyond prediction to active design, manipulating fundamental coherence.
But how? How can we actually manipulate these fields precisely?
That's the key question, right? UCTE provides a framework for this, too. It defines how the coherence curvature evolves under external perturbations, where O is the control knob, strain, doping, field strength.
And there's an equation for this.
A powerful renormalization flow equation, yeah. It captures the evolution elegantly.
It was AJA plus DG plus DGG. Can you break that down?
Sure. The first part, DEJA, describes smooth deformation. As you gently change your control parameter, say increase strain gradually, the curvature landscape smoothly reshapes, subtle tweaks, like kneading dough.
Okay, continuous change.
Right. But the second part, Nagia, that's what the real drama is. Topological jumps.
The jumps.
Yes, they are critical points, critical hypersurfaces. At these points, the bivector phase winds or unwinds dramatically. It's not smooth. It's a sudden quantized jump. Curvature monopoles can be created or annihilated.
And this changes the material fundamentally.
It flips its topological class, changes the churn integer. Imagine switching from a Ti to a while semimetal instantly. A phase change dictated by discrete shifts in the coherence landscape.
Okay, let's look at the control pathways. Starting with strain, what about small elastic strain, like less than 1%?
Just gently stretching or compressing bonds. This leads to isocurvature drift. AJ changes slightly, but the overall topology stays the same. A Ti stays a Ti, maybe just fine-tuned.
So fine-tuning properties. What if you apply shear or torsion, twisting it?
That introduces off-diagonal metric terms. It mixes the bivector components. You might change exia to exa, for instance.
And that leads to?
Potentially fascinating stuff. Possible spin-charge locking where spin and charge get tangled. Even emergent Ishii without TRS breaking a spin Hall effect without breaking time reversal symmetry. That's quite significant technologically.
But then you hit a critical strain.
Now things get dramatic. This usually causes band inversion at specific points in the Berlin zone. UCTE interprets this as monopole pair creation in K-space.
Like while nodes appearing.
Exactly. Two coherence monopoles appear and move apart. This drives a Ti into a while semimetal, or maybe a churn insulator. You get a quantized jump, Ishii, a designable switch for the material's topology.
What about really large compression?
Then you get lattice collapse of coherence channels. The structure changes significantly. Edgy can go towards 0 over large regions.
Leading to
a flat band condensate. Creating those flat bands we talked about, ideal for enhancing interactions. A potential pathway to high TC superconductivity. Imagine room temperature superconductors engineered by precise compression.
mind-blowing. Okay, pathway 2. Doping, X, adding impurities or carriers.
If you just inject carriers, electrons, or holes, you modify the occupation function, Fk. For small doping, the curvature is reweighted rather than reshaped.
So the landscape stays the same, but how electrons fill it changes.
Pretty much. Subtle changes to electrical response, no big phase transition usually.
What about isovalent doping? Swapping similar atoms, adding disorder but not carriers.
That introduces weak disorder, causing Gaussian broadening of A. The sharp features get fuzzy.
And if you add enough disorder.
You hit the percolative limit. This collapses coherence loops, crucial pathways for coherence. This can actually drive a TI into an anomalous Hall effect metal, a big change just from increasing disorder.
Add magnetic dopants, adding magnetic impurities.
They introduce extra bivector channels soon, their own spin interactions. And here's the cool part. When the exchange field from these dopants matches the material's intrinsic bivector gap.
Which happens at a critical concentration.
Right. Then a churn transition occurs. Again, quantized jump, C1, but linked to the dopant sublattice. You could literally dial in topological properties by controlling magnetic doping.
Incredible control. Finally, external fields. F, electric field. E.
Applies a minimal coupling BOAE OPEC. This effectively tilts the curvature ellipsoid in momentum space.
Tilting the landscape. Effect.
Leads directly to Edelstein spin accumulation, proportional to AO. This enables gate-controlled spin currents, turns spin currents on-off with a voltage, huge for spintronics.
Magnetic field B.
Causes a Zeeman shift of bivector eigenvalues. This splits curvature monopole pairs, causing wild node migration.
Monopoles move.
Yes. As they move, driven by the B field, they can cause anomalous Hall sign reversals. The Hall current floops direction, another dynamic control knob.
And the really cutting-edge one. Coherence field, eco. Like Kiet's pumping.
Exactly. Using structured light pulses, this involves time-dependent modulation of seat. You're directly wiggling the fundamental coherence field itself.
What does that do?
Produces dynamic curvature, KST with Berry phases, the result. Things like light-induced churn phases or coherent spin pumps, using light to dynamically create topological states on ultra-fast timescales or precisely pump spin opens up whole new areas.
So how do engineers actually do this?
Two main routes suggested. The first principles route. Use big computer simulations, DFT or TD-DFT, to calculate the block functions under strain doping fields, then figure out beta AC, differentiate to get IJA, and track the churn numbers C. Rigorous prediction.
Computationally heavy, though.
Can be. The alternative is the model Hamiltonian route. Encode strain, doping, fields into a simpler, coherent, two-band bivector lattice model. Faster for prototyping ideas.
So these pathways provide a practical blueprint for engineering. What did the source call them? Spin-charged coherence devices.
Exactly. Things like strain-activated while switches, doping-driven churn filters, light-tunable coherence engines, really advanced stuff.
Okay, let's zoom out again. What does this all mean for the future? What kind of applications can we envision with this new understanding of coherence curvature?
Well, it's not just theory, right? It's about practical, potentially revolutionary applications.
It feels like it moves us from just observing to actively designing materials based on this deeper understanding.
Precisely. The breadth of new pathways is fascinating. Engineering new materials, new types of quantum devices.
First, there's that idea of intelligent material design.
Right. Precisely engineering topological transitions, creating curvature-tuned devices, materials whose properties, connectivity, magnetism, information processing are sculpted by manipulating the coherence curvature.
Materials with built-in intelligence almost.
In a way, yeah. Design functionality, not just trial and error discovery.
And then coherence engines.
Harnessing those coherence fields directly. For energy conversion, maybe. New forms of quantum computing based on manipulating coherence, or even materials that change shape on command self-repairing, adaptive structures.
That sounds like science fiction.
Well, it's certainly ambitious, but the framework points towards it.
And crucially, there are pathways for experimental verification.
Absolutely paramount. The theory makes specific, measurable predictions. Spin Hall conductivity linked to torsion. Phase transitions linked to winding shifts. How perturbations offer control. These give experimentalists clear targets.
So it's testable.
Yes. And underpinning all this are robust computational methods.
The DFT-TD-DFT route.
Right. The ability to simulate and predict the behavior of these coherence fields using first principles calculations, evaluating bead and ASIA computationally. This drastically speeds up the discovery and design cycle, moving towards predictive materials science.
Okay, so we've taken quite the deep dives today into the unified coherence theory of everything UCTE applied to quantum materials.
We certainly have.
It's presented as this revolutionary shift away from conventional band theory towards a deeper geometry of coherence dynamics.
The underlying reality, according to UCTE.
We explored how spin is redefined not primitive, but a projection of that bivector coherence tensor. How coherence itself is the fundamental generative force, and how that core innovation, the coherence curvature tensor AJA, provides this unified explanation for a whole host of quantum phenomena. TIs, Wiles, the lot.
From a single framework.
And we looked at the detailed pathways for actually engineering and controlling these materials, strain, doping fields, envisioning this future of intelligent design and coherence engines.
Hopefully this deep dive has given you, the listener, a shortcut, a way into understanding this generative explanation of the full family of spintronic, topological, and coherence-active material phenomena.
It's definitely a bold, ambitious framework. Challenges fundamental assumptions about reality at the quantum level, showing how geometry and coherence might explain so much.
It really does tie a lot together, conceptually.
So, as we consider how coherence curvature could engineer new materials, new technologies, it leaves us with a final, perhaps unsettling question. What might it mean for technology and maybe even our understanding of reality itself, if consciousness is somehow entwined in the very coherence dynamics that define matter?
A provocative thought indeed. Something to ponder long after this deep dive ends.